All right, let's get started. Today, we are going to talk about matrix multiplication some more, do some more practice with that, and we have an application question with that, which we'll just kind of quickly look at. We won't really spend a whole lot of time on, and then I have a number of review questions that we can get through, or we can work on and hopefully get through today, and that will be it. Last class before the midterm. Announcements, exam stuff. I went through all of this in our previous class, the timing and starting scanning earlier. Yes, selfies, roommates. So I think we've covered all of this. If anyone has additional questions about the exam, then please ask now. Let's get all these other questions out of the way. Anything about the procedure? Nope. Okay, then I guess everyone's okay. Everyone understands what to do. The midterm prep, about just submitting a practice scan and then the side view, that kind of stuff. Most of you have done that. About 40 people have done that. There's still about 8 or 9 people who have not done either of those assignments. You should do those. They're worth points. They're just kind of free points for homework grade and everything. Will not be especially hard. And if we have problems with that on the midterm, then that's going to be a big problem. So I will encourage everyone to do that. Most people have. A few people, I wrote comments and I returned it. Like there were some problems and I said, you need to fix these things. So do that as well, if that's you. Okay, well, then let's get on with our material. So last time, we'll just do a quick recap of, we did this review last time. We'll just do it one more time here. So matrix essentials, if we talk about the dimensions of a matrix, how do we talk about that?
Row by column.
Right. Rows, then columns. So rows by columns. If two matrices are equal, what do we know about them?
The same size, the same dimensions, and the same numbers in positions.
Okay, so everything is the same. Dimensions, values, positions, everything's the same. Null matrix, what does that look like?
Components are 0.
Okay, everything's 0, and it can be any size at all. And an identity matrix, what do we know about that?
On main diagonals, we have 1, and it's a square.
Right, so it is a square matrix. So n by n matrix, or n could be whatever, but the number of rows, number of columns must be equal. All right, we will talk about briefly today why we care about a null matrix and an identity matrix and where we put those into use. So transposing, adding and subtracting, scalar multiplication, matrix multiplication. Those are the 4 core operations for dealing with matrices that we should be familiar with. So matrix multiplication, I gave a long kind of careful explanation of this last time. I'll just give the same kind of overview, but just a brief version of that right now. So it's a little weird. It's not what you would like necessarily guess if you were to guess what it means. So we have 4 positions in this case, 4 different values that we have to calculate. So the basic idea is we do each row of the first one times each column of the second one. So first row in the first one times the first column, and then again times the second column in the second matrix. Then we go to the second row of the first one and times the first column, then times the second column, and then the third and the fourth and until we're done, until we've done all the rows and columns in the matrix. And where do we put the values? Well, we just kind of see where everything lines up. So the red one, it was the first row and the first column. Where's that overlap? It's right here in the middle. So that's where we are going to put the value. So the way I was showing you of doing this with sort of one on the left and the next one on and the second one on the top, and then the results kind of down below that, that way makes it easier to line everything up and makes it harder to make mistakes in your process. Once you have some experience with this, you probably wouldn't write it like that. You would just kind of already see like what things are lining up and what things need to be multiplied, and you just write your answer directly. But when you're starting with it and still kind of getting used to how to do it, that way is very useful. So let's do some practice with this. We'll start with this one, I times E. So here's E. What is I?
Identity matrix.
Okay, so I is a special letter. It is reserved for the identity matrix. Other matrices could be any other letter, A, B, C, whatever. But if you see I, it's not just some random matrix. It's very specifically an identity matrix. So the operation we are doing is I times E. E here is a 2 by 2 matrix. So if E is a 2 by 2 matrix, what size of identity matrix must we be using in order to make this operation work?
2 by 2.
All right, so it also must be a 2 by 2 because we match the inside numbers. If this one, the inside number on E is a 2, then I must be a 2. And we also know that I is also always a square matrix. So therefore a 2 by 2 matrix like this. So I, when you see something, some matrix times I, you have to look at what size it would need to be in order to do the operation. And then that's the size of I that you use. The problem isn't going to tell you, hey, guess what? It's a whatever, it's a 3 by 3 or something, or a 10 by 10. You can figure that out just by looking at what the dimensions are of the other matrix. Okay, all right, let's actually, or while I'm writing this, I want you guys to think and try to guess what size do you think the result will be? If we take an identity matrix times E, sorry, not the size. Size is the 2 by 2. What do you think the result will be? What will the final matrix look like after we do this multiplication?
A 2 by 2 matrix.
Okay, so that's the size, but what about the contents? What will we, when we look at the results, what will we notice about it?
It's the same as the original one, I guess.
Which original one?
The E matrix.
E. Okay, so if we do this multiplication operation, our results will be E. So E times something will still just equal E at the end. All right, let's try that and we'll see what happens. So if we are doing our matrix multiplication here, remember we, let's do blue. I got to draw this one edge. So 2 by 2 matrix. Let's kind of line up. There are the 2 rows. there are the two columns. Sorry, before we do that, another way that we can check if matrix multiplication is possible. So this is the number of columns in I, the first matrix, 2, and number of rows in the second matrix, E. Just do they line up kind of, does each thing have one match and is it an equal number? If yes, okay, I don't know, it's like a little rainbow or something there. Then it works, it's going to be possible. So another advantage to writing it like this, you can also do a second check to know if it's actually possible or not. Okay, so how many positions do we need to calculate? Just line all this stuff up. 1, 2, 3, 4. Each of these points of overlap represents some number we have to calculate. All right, let's do the first one. So first row and first column, what plus what? What numbers will we put here? What plus what?
1 plus 0.
1 plus 0. So 1 times 1 plus 0 times 0. Excuse me. That is our process for matrix multiplication. So multiply each of the matching things, and then at the end, add them all up. And then all of that is just one position. Okay, let's erase. That's our next position here. What will we have?
-4 plus 0.
Okay, so -4 times 1, so -4 plus 0 times -9, that's just 0, so there. Okay, and we can move on to our second row here. Second row from the first matrix, again, times both columns. What numbers will we get in here, the second row?
0 plus 0.
0 plus 0, okay, and
0 plus -9.
0 plus -9. So 0 minus 9, but I'm writing it as the -9 just for complete sort of clarity here. Okay, so those are the values in those cells. So let's actually just write out here what it will be. So I times E, therefore, is equal to, we'll just do the addition here, 1 plus 0, 1, -4, 0, -9. And what do we notice about this?
It's the same as the E matrix.
Same as E. Okay, so identity matrix, that's a special property of the identity matrix. Identity matrix times anything will give you just that same matrix back. So it doesn't actually change what we are doing. It doesn't actually change the matrix that's going in. So 1, -4, 0, -9, which is also equal to E. So I'll talk a little more about this and kind of some theory things to this. What do you think would happen if we did E times I, if we reversed this? Still multiplication, but in the other order. What would our result be?
Isn't it still the same?
It would still be the same. I know I told you last time, if with matrix multiplication, if you flip the order, you change the results, except for the identity matrix. Identity matrix is the exception to that. So it's a special matrix, a special property. So I times E is equal to E times I, which is also equal to E. This is identity. So let's, you might now be thinking, well, what was the point of that? If the result is just the same thing that we started with, why did we bother doing that? So I'm just going to move this stuff over to make some space. There. Okay, so let's think. Let's talk about this idea of an identity. We'll start simple. There we go. So let's say I have some variable a, and we have this operation which we define as plus, so addition. So a plus what equals a?
Plus 0.
0.
Plus nothing.
So a plus 0 equals a. So we have this operation, and we have the special number 0, which we can put into this operation. And even if we do this operation, we still get the same thing back. We still come out with a. So this here is called the additive identity. Let's write this down here. Identity. Additive identity. Because adding that number doesn't actually change what the other one is. So a plus 0 is still a. This is really important for defining math operations. So it's a little bit of a theory discussion here. If we make up some new operation that we can do with numbers, so whatever operations we have in math, then we need two things. We need to have an inverse operation. So for addition, the kind of the opposite thing is subtraction, obviously. And we also need this identity, where you do this operation with this special value, and it doesn't actually change the original number that went in. A plus 0 is still a. We use this in a lot of places. Like if we had some equation and on the right side and the left side of the equation, so whatever, plus 5 equals whatever, plus 5 or something. We can do this, right? We just say, let's add 5 to both sides of this equation. Why is that possible? Well, it's because what we're actually doing is whatever plus, and then on the other side, it's plus 5 minus 5. And plus 5 minus 5, that's the same as saying plus 0. And we know that 0 is the identity. So adding that doesn't actually change anything. So it's okay to be, that's why it's okay to be adding 5 to both sides like this, because it doesn't change anything because it is equal to the identity. So lots of kind of theory stuff in terms of set theory as a formal field of this. Okay, so for multiplication, let's try this. A times what equals a?
1.
1. So obviously, a times 1 equals a, and then we can do the same thing here, same discussion. So multiplication, division is obviously the opposite of that. So if we want to do like times 5, like some equation, we want to multiply everything by 5, both sides. Well, that's because times 5 divided by 5 like this, and then that's the same as saying just, well, multiply by 1, and multiplying by 1 doesn't change anything. So this one here is the multiplicative identity. So for this operation, which we call multiplication, 1 is the special number that doesn't change the number that went in. It doesn't change what the result will be. So it's still a. Okay, so that's just some little basic background stuff. For matrix multiplication, yeah, so I'm gonna have to erase some of this. For matrix multiplication, the identity is the identity matrix. So whatever matrix A times I, identity matrix that where the size matches up to be able to do it, that is equal to A. And that's also equal to matrix I times A. We can flip the order, just adjust the size perhaps, and then we'll still get matrix A out. So for matrix multiplication, this I with ones in the main diagonal, zeros everywhere else, and square, that will give us the same result out, this matrix A, whatever it is. So that's why we care about the identity matrix. That's why it's important. And then there are a whole bunch of practical applications. The main one here is with inverse matrices, which I have not shown you and I haven't explained, but that is a thing. It's like, that's probably like the next step if we were to do more with matrix operations would be this. So this identity matrix, this idea of it is very important. And understanding that any matrix times an identity is still that same matrix is also a very important idea and is used in a whole bunch of math things, a whole bunch of operations with matrices. Our other one for matrix addition, so some matrix A plus we don't really have a fancy symbol for it, null matrix, the one where it's all zeros, that will equal A. We just adjust it to be the proper size. So the null matrix is the identity for matrix addition. And then, but we have a special name for it called null. So the identity matrix is specifically this one for matrix multiplication. So that's why we care about this. That's why we're talking about this identity matrix. It is, and then this, not just theory, this comes up with a whole bunch of practical applications, which we don't have time to see in this class, unfortunately, but they exist. You can just kind of trust me on that. Or when you go like just slightly further with matrices, that stuff all comes out. Okay, that's why we care about null and identity matrices. Anyone have questions about that they want to ask? I know we don't really do theory discussions very much in this class, but that's to want to explain why we care about those things. Okay, let's do the other operation that we have here, E times F, and then whole thing transposed. So you can do that right now. Try that on your own while I am writing out things here and getting this set up. And we'll see if we get the same result. So E times F, then transposed. Go ahead. So I'll answer your question in just a moment once people finish working. All right, I am ready. I hope you guys have done at least the setup and most of the calculations. So let's check. E times, all right, sorry, let me answer there's a question in the chat. Sorry, it's a private message. If you ask it publicly, then everyone else can see the question too. Is the null matrix always a square matrix like the identity matrix? So I answered that when we had the previous thing. Null matrix can be any size, whatever size it needs to be in order to add to whatever thing. So if we have some, I don't know, like a 3x5 matrix, that's A, and then we are adding, we want this like additive identity, then okay, then we need a null matrix that's also a 3x5, because for adding, they have to have the same dimensions. So null, any dimensions at all, just kind of matches up with whatever it needs to be for whatever you're adding or subtracting it to. Okay, so identity must be square, null can have any dimensions. Okay, so let's go back to this question. E times F dimension, is this operation possible?
Yes.
Yes.
Yeah, because same as the ones we saw before, it's a 2x2, 2x2, so both square, yes, it's going to work. Inside numbers are 2, outside numbers are 2, so that's what the size will be. All right, 2x2 matrix. You know, we could line everything up like this, but I'm not going to write those. Hopefully we can start just seeing in our minds what things line up and where they all should go. So first position, can someone tell me the numbers? What plus what?
4 plus 28.
4 plus 20?
28.
28. 4 plus 28. All right, next position here.
3 plus 0.
3 plus 0. Next one.
0 plus 63.
0 plus 63 and
0 plus 0.
0 plus 0. Okay, so there is our result. We'll just kind of do the actual adding here. So EF therefore is 4 plus 28, 32, 3, 63, 0. Okay, so we have E times F. We're not done though. This question is asking us to do this and then transpose it. So we should take 32, 3, 63, 0, this matrix, and transpose. And if we do that, what will we get? What's our-
32, 63,
Okay,
3 and
so
0.
32, 63, 3, 0. Remember, for transposing, we just take first row, rewrite as the first column, and take the second row and rewrite as the second column. And that's it. Okay, so there is our results. This thing here then is EF transpose. Done. All right, I have some more practice questions, but does anyone want to ask about this operation, what we did here? Okay, so let's go on. We looked at these ones last time. I won't repeat the whole operation. We'll just talk about what we discovered when we kind of looked at what happens when we change the order here. So we calculated A times C, and then after we calculated C times A. What did we notice when we did that?
Different results.
Different results. So A is a 2x2, C is a 2x2, So in both directions, the operation was possible, but the numbers that we got out were completely different. Not slightly different, not like flipped over or anything, just totally different numbers, like basically no connection at all. So changing the order for matrix multiplication completely changes the results that you'll get. So that was our first thing. We also did A times B, and we noticed B here is a 2 by 3 matrix, A times B, and or let's talk about that one first. A and B are different dimensions. So what happened with our operation?
The result was 2 by 3 system.
Okay, it was a 2 by 3 matrix. So 2 by 2. Inside numbers were the same, so it was possible. And the outside numbers here were telling us the actual size of it. Excuse me. So even if your matrices are different sizes, it can still be possible to do matrix multiplication. So that's the weird property. Matrix addition must be the exact same dimensions. But matrix multiplication, they can be different sizes. Won't work out every time though, which is what we discovered. B times A. What happened when we tried to do B times A?
We couldn't
It's
do it.
impossible.
Okay, why not? What happened?
We stopped at some point because we have some unknown value.
B times 2 times 3 and 2 times 2, 2 by 2. Okay, so the inside numbers didn't match, which we discussed and said, okay, that's why it's not going to work. But B was a 2 by 3, A was a 2 by 2. So number, like this. And we noticed, okay, well, the first value would be multiplied with the first value there, second value there, second value there, great. But we have a third value, this 2 in the first row of B, and it has no partner, nothing to multiply it by. So as I said before, if there's like a number missing, if we need a number there and it's just empty, the matrix doesn't go that far, we never assume that it's a 0. We just stop the operation. It's not possible. B times A is undefined. And then this here, because the third value would not have a match with matrix A, that's exactly why it's undefined. Okay, so changing the order can also change if the operation is possible in the first place. It works in one direction and totally doesn't work in the other direction. So another unusual and perhaps unexpected result of matrix multiplication. So I had that summarized here. Order, very important. So the conditions, matrices can be different dimensions, but number columns of the first matrix must equal the number of rows in the second matrix. So if we have these matrices A, B here, columns of the first one is n, rows of the second one, B is P here. If these two numbers are the same, if we can connect them and there's, I don't know, like some little smiley face there, okay, then yes, it will work and the operation is possible. And then what will the size be? Well, it's the two outside numbers, M and P. There's our second smiley face or upside down rainbow, I don't know, however you want to remember it. That will tell us the dimensions. The result will be an M by Q matrix, the two outside numbers. So writing out the dimensions with rows first, then columns in that order is very important to be able to do this checking process properly. So that's how we know if we can actually do the operation or not. All right, let's try some practice questions here. There we go. So I have matrix G and H here, and I want to do G transpose, sorry, yes, G transpose times H transpose, and then also H transpose times G transpose. So take some time right now, try to figure out, are those operations possible? What would the size of the result be, the dimensions? And then what's the actual result? What are the actual numbers in that? So please try to figure out as much of that as you can right now while I set up everything for us. All right, let's try these out. So first we have to figure out what is G transpose and what is H transpose before we can talk about sizes and actually doing the multiplication stuff. So what are the dimensions of G transpose?
1/3.
Okay, it's a 1/3 matrix because G is a 3/1 matrix. Transposing, we'll just flip those. So it's a 1/3, and tell me the values here.
1,
1, 2, -2.
1, 2, -2. So I know this particular one, it might feel like, okay, we're just rotating it, but that's not what's happening. So we'll see that with our second one here. So H transpose, what are the dimensions?
2/3.
3/2.
3/2. H is a 2/3, and when we transpose, we will get a 3/2. Okay, so 3/2. Tell me the first row here.
0.
1, 2.
1,
0.
0. Second row.
1,
2, 1.
2, 1. And third row.
0, -1.
0, -1. Okay, so remember transposing, we can take, so first row, rewrite as first column, or we can do first column, rewrite as first row. It's the same thing. So here we can see it's not a rotation, it's this whole diagonal flip along the main diagonal. So here's our H transpose and our G transpose. So now we can try to figure out if these operations are possible or not. So we have a 1/3 matrix multiplied by a 3/2 matrix. Is this operation possible?
Yes.
Yes.
Yes, so 3, 3 matches up. There's our little smiley face. Yes, it works. How large will the result be?
1/2.
1/2 outside numbers. There's our second little smiley face. Okay, so when we do our lining up and everything, our result should be a 1/2 matrix. If it's not, then we've made some really big mistake somewhere. So G transpose is a 1, 2, -2 matrix. H transpose is 1, 0, 2, 1, 0, -1 matrix. All right, so very small result we're going to have down here. We'll still, normally we would kind of skip the whatever, like this plus this plus this thing, but just again, so we can all see very clearly what's happening. First position, please tell me what this is. What plus what plus what?
1 plus 4
1 plus 4
plus 0.
plus 0. Okay, so I'm going to write out the 0 so people can see what's happening. So 1 times 1, 2 times 2, -2 times 0, 1, 4, 0. Second position, what are the values? What was
0.
Yeah.
2
0
0.
plus 2
plus 2.
plus 2. -2 times -2. There we go. So our result here then, G transpose times H transpose, just add those together, 5, 4. So there's our results. Very small matrix, just 2 positions, 5, 4, 1/2 matrix. All right, let's do this for the other one here. H transpose times G transpose. H transpose is a 3/2 matrix. G is a 1, G transpose, it's a 1/3 matrix. Is this operation possible?
No, it's impossible.
No, because the inside numbers don't match here. So we can skip all this, like trying to do the calculating and then the finding the thing that doesn't have the match. We just look at the inside numbers and say undefined. And we can even add a reason here because columns of H transpose not equal to rows of G transpose. So the number of columns and the number of rows don't match. Number of columns of the first one, rows of the second one don't match, so impossible. Just a little note here, on an exam, and this would be stated very clearly. Also, the practice questions in our textbook, and we'll be going over some of those, a bunch of those in the workshop this evening. If the operation is undefined, then they ask you to give some kind of reason for it. And I will do the same thing on an exam because I don't want people just like guessing undefined, undefined, undefined for all the matrix questions. You have to show me you actually know that why it is undefined and you're not just randomly guessing. So just some kind of brief explanation, columns of this don't match rows of that, doesn't work. If it's matrix addition, the two matrices don't have the same dimensions, so not possible. So don't need like a paragraph, but just some little short thing to show me that you actually understand why it's not possible. Okay, so just a little note, but requirements like that on a test or exam will be very clearly described on the exam itself. Okay, any questions about these two operations? Nope. Okay. We'll erase most of this. I just want to extend one little thing that I talked about before. Let's see if we just understood it. Get rid of all this. Let's look at matrix H, which is a 2 by 3 matrix. If I want to do matrix H times I, so times the identity matrix, what size must the identity matrix be?
3 by 3.
Okay, so a 3 by 3. So if we're going to do H times I, in this case, I must be a 3 by 3 matrix because the inside numbers need to match. If I'm going to do I times H, what dimensions must I be?
2 by 2.
2 by 2.
2 by 2 here, because the inside numbers need to match. So that's kind of a weird thing. Multiplying by the identity matrix in either order, the result will simply be matrix H, but the size of the identity matrix we're using, it might be different. So we adjust the size to be whatever will make matrix multiplication possible. Okay, but when we flip the order, we might have to use a different size. That's just a little, like, we understand the logic behind that and the reason with matrix multiplication and inside numbers, but still the results might be a little surprising. Okay, let's go on to our practical example here. We're not going to do, I'm not mean, we're not going to like actually have to calculate this whole thing and do, like, I'll just show you, we'll go up to the step of when it would happen and then we'll just kind of skip from there. I just want to show you how this would work. So matrix multiplication, it does have actual, like, lots of applications. So let's look at this data we have here. So some bookstore. So some like chain of bookstores, store one or store ABC like this. And then here's a list of all the books that they sell. So I only wrote 4 because I don't have too much space here. But you know, realistically, a store would have, their product list would be like hundreds or thousands of products, right? So a bookstore has like thousands of books in it, of like different kinds of books. So here's a table showing all the books, all the products, and the prices for all of those things. And here is a table showing the sales numbers, how many of each of these books they sold at each of these different stores. And the question is asking us, let's try to figure out the total revenue for each of these stores. Okay, so total revenue, what's our formula? TR, how did we calculate total revenue?
Profit plus total cost.
Right, P by Q. So P is the price of the products, the price that the consumers pay, and Q is quantity sold. So look at the things that we have here. So this is a table of all of the prices that consumers would pay. That's kind of P, right? And then this other one, sales, the sales number sold, quantity sold. Actually write this a little higher. Q. So it's kind of working, right? Like P times Q, except now P, it's not just one number, it's a table of values. Does this table of values, these numbers in a box, does it perhaps look like something? Do you think we could change it to some kind of math concept, perhaps?
It can be a matrix.
It's a matrix like this. This is a 4 by 1 matrix. Q here, just look at the numbers. That is a 4 by 3 matrix. Okay, so total revenue, we could do this, and we want to multiply P by Q. Almost. There's a problem here.
The number of columns of the first matrix, it doesn't equal to the number of rows of the second matrix.
Okay, so the inside numbers don't match up. Can you see a way that we could fix that problem?
Transposing.
All right, transpose P. That's why we care about transposing. So let's do that. And now P transpose is a 1/4 matrix, like this. So it'll work. We can do the matrix multiplication. What will our resulting size be? Resulting dimensions?
1 times 3.
A 1/3 matrix. We want total revenue for each store. So we'll get 3 different numbers, 3 stores. That sounds about right. And if we multiply price of each book times quantity sold of each book, matching up the number, it looks like it's going to work out. It looks like we would just be adding up total the revenue values for each individual book for the entire store, and then one number that is total revenue for that store. And we'll have 3 numbers total. So that looks like it will actually accomplish this for us. So if we were to rewrite this a little bit to show kind of the way that we normally looked at these, So matrix here, and then we would have our results down here. Okay, kind of line up the rows, line up the columns, 3 positions like that. Multiply the first thing times the first thing, multiply the second thing times the second. Okay, I think you get the idea. It's a table, but we can just interpret this table as a matrix and then do all the matrix things with that table. Okay, so in case it's not like wasn't super obvious already, then this would be the thing that we could do. P transpose times Q, and we would get our results. I'm not going to make us actually do the calculations. It's just going to take a bunch of time, but I think you get the idea. We can do this, use these operations like this. Now, little discussion. If you were asked to figure this out by hand, you would almost definitely not use matrices to like just do the manual calculation on paper or something. But any modern company isn't doing this by hand. They have spreadsheets. They use Excel or Google Sheets or whatever, and they have spreadsheets to do all this. If you were going to do this with a spreadsheet and again, thousands of products, maybe 10, 20 different stores, you're not going to like manually write out a little formula for each thing times each other thing. That would take forever. So you can just go to your table and say, okay, this part of the table define as matrix this, define that part as matrix that, and then just one little operation, P transpose times Q, you can actually be doing hundreds or thousands of little multiplications and additions and everything, and then calculating these big results. So this matrix multiplication, it has a very significant kind of convenience factor to it, or benefit. We can actually have tons of individual multiplication and addition operations happening inside of this. And at the end, we just get this nice clean results, and very easy to talk about, very easy to write a formula for this, very easy to represent. So convenience is one major advantage that we get with matrices. That's one big thing. So just anytime you're dealing with huge data sets, any kind of like big data analysis, or you're trying to put your information into like some statistical programming tool, which we have as like one of the specializations at SolBridge, like doing programming with R or SAS or SPSS or something, giant data sets. Okay, you're turning them into tables, into matrices, and then doing sort of matrix operations with it. If you've ever done programming of any kind and you've worked with arrays in a programming language, that's a matrix. You can do all the matrix things with that array. Spreadsheets are just basically a giant matrix. It's the math concept turned into just a computer program. Specifically, the whole kind of math side of things, microeconomics. I don't know if you guys will see this in your current micro econ class or not, but if you go a little further in micro, there's input-output tables, which are I'm not going to try to explain these things now because I can't briefly explain them in a way that would actually be memorable, but lots of applications of this. We have talked about constrained optimization a little bit before. Macroeconomics as well, these things called ISLM models or comparative. I'm not going to try to give some big explanation now, but widely used, matrices are widely used in a whole bunch of post-high school mathematical fields and like engineering and sciences and stuff. And yes, business and economics and everything as well. So they're rarely used in the high school level, not for anything practical that I've ever noticed, but for lots of post-high school fields, yes, matrices are a widely used tool. So your later professors will actually do these practical applications with you, but we are just doing the basic idea of what these matrix operations are. Just want to give you some sense of, yes, there was a point to this. Yes, this is actually practical and useful to know. Okay, that wraps up our discussion about matrices. There's lots more we could do with them, lots more theory and everything. In like a math program, like matrices would be an entire course, but we just did this little sampling here. I want to move on to some other review. I don't know how much, I have a bunch of different questions here. For sake of time, we might not like actually solve all of these, but just talk about quickly how we would solve these and then move on. Okay, take a moment, just read what's here, and then we'll talk about how to solve it, and then we will move on to the next question. For question A, find the equation of a line that goes through points A and B, point A, point B here. How can we figure that out?
We should use a formula.
Any formula?
No,
Tell me specifically.
is it delta y divided by delta x? No.
What does that tell us?
The m, the coefficient.
The slope.
Slope. Okay, so let's just clearly say what m is representing.
Slope,
So
yeah.
slope we can get from this, and give me a little more detail about how to use it.
Y2 minus 1 minus y1 divided by x2 minus x1.
X2 minus x1. And the 2 and the 1, we are just kind of randomly defining. Let's say B is 0.2 and A is 0.1. We just pull out, okay, that x value, that y value. So what is the delta, the change in y relative to change in x? Okay, and that would give us slope. So that equals whatever number. Then what do we do?
Then we write the equation of a line, which is y equals m times x plus b.
mx plus b, okay.
We put my, we just choose a random point. We put the coordinates of this point into this equation.
Random point?
A or B, we can choose.
Okay, so
From these points.
one of the points that we know is on our line. So we
Yes.
have we do our slope thing and figure out, okay, here's the m value. And then we will look at, let's say, point A or point B, any point that's on that line. And we will substitute those values into, let's say, this x and this y. Those values we substitute into this equation here. So that would give us something equals m something x something plus b. And then we are just calculating, okay, what's the b? What's that intercept, that last value there? And then we have m, we have b, and that gives us everything we need for the equation of a line. Okay, so that's our process. I don't want to go through solving the whole thing because I want to leave this for you to be able to practice. Question B here is asking us a line that goes through B and is perpendicular to AB. How can we figure that out?
First, find the negative reciprocal of the slope of AB, and then write the equation of line and then substitute the coordinates of B into the equation.
Okay, so if the slope of AB, whatever that is, then we are going to just take the negative reciprocal. So 1 over, so then our perpendicular slope, so our targets, let's say our M2 here, is 1 over whatever the slope is for AB. So we just, sorry, negative reciprocal. We flip over the fraction, change the sign, and then that gives us the perpendicular slope. So we'll have, again, our y equals mx plus b. And then there's the m value. And then it's going through point B. So just take the x and the y values for point B. So it's what, 1 and 6. And we just substitute those into those values and calculate our b. There's the m, there's the b. We can build our equation on that. Question C, parallel. What do we have to do? Parallel to AB.
We have to substitute the same slope of AB.
Okay, so parallel means same slope. So our slope, let's say 3 here, this is equal to then slope of line AB because it's a parallel line. So there's the slope, and then once again, use point B, the coordinates for point B, sorry, point C, the x and y values, and calculate our b value for that one, mx plus b. And then there's the m, there's the b, there's the equation of the line. Okay, so that's the process for this. So 2 points, can you find the line that goes through them? And do you understand what perpendicular slopes are? Do you understand what parallel slopes are? What's the relationships between them? All right, next question. Again, we won't go through these. I think we'll spend some time on the break-even question, but these ones are a bit easier. These are from a while ago, so don't want to spend too much time on these. 2 equations of lines here. So 2 equations, 2 unknowns. How can we find a point of intersection?
By using the point of substitution, the method.
Okay, so we can do substitution. Can you just briefly explain what substitution is?
Yeah, we're gonna find one unknown variable and then substitute it to another equation, and then solve it.
Okay, so we isolate one variable. In this case, y is already isolated. Y is on one side, move everything else to the other side. And then we will substitute that in to that same variable in the other equation and just simplify, and you'll solve for one of the variables. We would solve for x in this case. That's substitution. And we can also do the one on the right. Seems like it's set up nicely for something else.
Elimination.
Elimination. How do we do elimination?
We target one of the variables and then try to isolate it by adding or subtracting the whole equation.
Not isolate, we eliminate it. So let's say if we took let's say we target the x and we want to get rid of the x's, then we would multiply the second equation by 4. So 4x minus 8y minus negative 80, sorry, equals negative 80. And then we take the two whole equations and then one equation plus the other one or minus the other one. And then that will eliminate one of the variables for us. So multiply one equation by something else to make your coefficients match up, then add or subtract the two whole equations, and that will eliminate one variable. Simplify and solve for that variable. So substitution or elimination method, we should be comfortable with both of those. Reading things on a graph. Can you tell me what the point of intersection would be of these, or sorry, tell me how we would find the point of intersection of these two lines?
Just using the graph.
Okay, how?
Well, I was actually asking.
Use whatever methods you want. However, but the graph here does not actually show the point of intersection. So how can we figure it out?
We can actually find the equations of these lines.
Yeah.
Okay,
Just using the graph.
how do we do that?
Okay, so the first equation is minus 2x plus 2.
Okay, give me the explanation of how you're doing this.
Okay, so to find the b, we need to find the intersection with the y-axis.
Intercept, but yeah.
Intercept, yeah, intercept.
Okay, so there we go. It's 2. B is 2. All right, and what else?
We need to find the slope.
So, all right, and how do we find slope?
It's so hard to explain.
Rise of run.
Okay, the same thing we did before, remember? The delta y over delta x, just choose 2 points. So here's point number 1, here's point number 2. This is point 0, 2, and this point here is 1, 0. Very easy points to work with. Or here's another point, here's another point, here's another point, here's another point. Whatever points we want, and then we just determine our, excuse me, any 2 points will let us do our slope formula, our delta y over delta x, and that will give us the slope. There's m, there's b, we have the equation. What about the blue one? So we can do the same thing for slope, and we can identify some points. That looks like a point right there. Not all these are cleanly lining up, but that one looks like it does, and that one. Okay, here's 3 different points on the line, so I can figure out slope, but we don't see the y-intercept. So how could we figure that out?
By substituting the values into the equation and then finding the m.
Good. Not m, we would have m.
Sorry, b.
B, right? So y equals mx plus b. The same thing we just saw 2 slides ago. If we have m, and the only thing we're missing is B, we can find B with any point. We don't need to see the y-intercept directly on the graph. Any point we can substitute in the y and the x values, and if we already know the slope, then we can find out the y-intercept very easily. So if you can find 2 points, then the rest you can do with algebra, the same as we saw with 2 slides ago. In these questions, you can also look at the graph and understand what the slopes are going to be roughly. Okay, positive or negative, bigger than +1, or kind of more negative than -1. Just like roughly what region it should be in, and then that will let you kind of confirm your calculations. Okay, all right, 2 more. Let's do this one really quickly. Just talk about how. If we're trying to solve for x, y, and z here, what do we do?
We target
We can use matrices.
Okay, so we could just do our kind of regular substitution we talked about before, substitution. And we could also do our kind of regular elimination. But if it's a larger system, definitely, yeah, matrix elimination, or sort of Gauss-Jordan elimination, can be faster for us. Elimination. So if we were doing it that way, we would just create a matrix from this, -3, 1, 1. That's not enough space. -3, +1, +1, -4, -1, 2, -2, 1, 2, -1, -1, -1. Okay, there's our matrix. And what would our goal be? What kind of shapes would we be trying to make?
We need to get the identity matrix.
Okay, so our final version would look like that identity matrix. So with a 1, 1, 1, everything else zeros. I drew this a little too big. And the difference from the identity matrix, it would be we'd have some values here on the far right column, but the rest of it would look the same as an identity matrix. That's the final version. What's the halfway version?
To get zeros in the left bottom corner.
Okay, so that triangle form. So 1, 1, 1, 0, 0, 0, and then some values here, like this. So we start with the box shape, lots of values here, then we go to this upper triangular form, this triangle shape, and then we go down to just the main diagonal. That's kind of the process. So, and we talked about its elimination. So we're still just multiplying rows by a constant and then adding and subtracting rows. And we can also swap rows. We talked about those various matrix elimination operations that are possible. Okay, that's that one. So again, just these are the strategies. Hopefully that is enough reminder, and you can work through these on your own. The last one I had here was this break-even question, which I was hoping we'd have some time for, but not apparently. Tell me how we solve break-even questions. What's our strategy?
DCTR and profit equation.
Okay, so we calculate our total revenue. Total revenue is equal to what?
PQ.
P times Q. So the price that the customers are paying times the quantity sold, that's Q. And TC, what does that represent?
The
F6.
materials.
Okay, so TC is total cost. How do we
Yes.
determine total cost?
Cost plus.
Total revenue minus profit.
Not if we don't know profit already.
Cost.
FC plus VC.
Okay, so our variable costs plus our fixed costs. So variable costs plus fixed costs. How do we figure out variable costs?
Q multiplied by the variable cost of 1 unit of
Right, sort of kind of our unit cost. So how many things did you make times what's the cost of making each one of those things? So cost of making one thing times how many of them you make, there's your total variable cost. So variable costs vary with Q. If Q goes up, the cost goes up. If Q goes down, cost goes down. Plus the fixed costs, what are fixed costs?
Costs.
60,000.
Okay, so in this case, it's 60,000. Fixed costs are anything that don't vary with Q, that are not dependent on Q. So in this case, it's telling us just the cost of running a print shop, because you have to pay the people who work there. You turn on you have the electricity to run the machines, and you have the maintenance people on standby in case something breaks and whatever, safety people. So just upfront costs that are independent of the number of units you produce. So those are fixed costs. All right, and then profits is what?
TR minus TC.
Right, total revenue minus total cost. Okay, and then that's just how we determine our profit. How do we figure out what is a break-even point first, and then how do we find it?
When profit is 0.
Okay, so break-even is the point where profit is equal to 0 by definition, where when you start, your costs are high and your revenue is 0, but then as you produce more, hopefully those two they'll catch up. The revenue will catch up the costs, and you'll have a profit of exactly 0. So to find it, okay, profit is 0, which means that I don't quite have enough space. So 0 then is equal to total revenue minus total cost from our profit equation. And then therefore, total revenue is equal to total cost. And you just simplify and figure out, here's the Q value. Q is equal to this, whatever that number is, that's the break-even point. If we make that many things, our profit will be exactly 0. Okay, so those are the strategies. I'll post these particular slides from these review questions on our classroom page, so you can try to actually go through the solutions here on your own. If you're having trouble with them, come back and listen to this and the strategies. That should be enough for you to be able to work through these. If it's not, you might have to go back and look at some previous examples about like with the full solutions and then try these again. Okay, 10:20 overtime again. Hopefully we are feeling well prepared and confident, and we can ace the midterm, maybe. There is another workshop this evening, so a whole bunch more of matrix scalar multiplication, addition, and matrix multiplication questions I will do in that workshop this evening at 7:30 if you want more practice with that. Otherwise, you already know what the content is for the midterm. It's everything that we've done up to this point. all that setup should be done. If you have roommates, or if you have a roommate, then fill out that form, and you need to let me know that in advance. Otherwise, I think we are ready. Does anyone have a question, something they want to ask before we wrap up?
Professor,
Yeah.
and I sent you an email on Tuesday, and it's about I'm currently in China.
Yes, yes,
so
yes. I will be emailing the students who are in China, and like, here are the backup methods. I haven't emailed yet, but I will do that soon.
okay, thank you, Professor.
All right, so let's wrap up here. If you have more questions, just hang around and ask. Otherwise, I might see you this evening for the workshop. If not, good luck with all your studying. I will see you on Monday evening for the exam.
Thank
Goodbye,
you,
everyone.
Professor.